Okay, so continuing on with basic concepts, we've talked about the movement of charged particles through a medium as being current. So that movement of those particles requires energy. It requires work to be performed. So that's where the idea of voltage comes into play. So let's first consider that generic element again. Okay. And again, I'm defining that element as being something that can manipulate the motion of charge, or in other words, current, through it. And we're going to define this element as having two terminals. So we know that, and that's what these lines here are, the two terminals. Terminals, and this is our element that is performing some function on our charged particles. So we know that based on the conservation of energy, what goes in must come out. So if I define current I going into that element, current I1 must also come out. Current I1 going in must come out. But the movement of those charged particles in the form of I going through that element must require some work. And that's what we define as this potential difference between the terminals. And so if I call the terminals A and B, some energy is going to be lost as I move the charge from A to B. So that's what we quantify as the potential difference of V across it. And we give it a polarity of positive and negative with respect to the negative in order to describe the potential loss of moving those charged through that element. Okay, so voltage specifically can be then defined as the energy required to move a unit of charge from one reference point. So in this case, we'll say B, since that's what we're calling the negative terminal, because charge again is going to move from the negative to a positive. The positive polarity is going to attract the negative charged particles. To another point, in this case, A. So this is measured in what we call volts, capital V. So we can write that mathematically then as energy required to move, so delta energy required to move a unit of charge, dq. So 1 volt is going to equal 1 joule per coulomb. So just like current had to have a magnitude and a direction, voltage has to have not only a magnitude but a polarity. So this is very important because it describes that energy potential difference between 2 points arbitrarily. So an example that's given in the book, and I'll do that one again, is say we have an element that we've defined as being between points A and B. And arbitrarily, if I find that A is 9 volts higher in potential than B, I would write it this way. So A is 9 volts positive with respect to B. This is equal to the definition that A is negative 9 volts with the polarity that A is negative and B is positive. So B is negative 9 volts higher than A. That's kind of a weird way to describe it because you've got two negatives there, but either definition is correct. Because what's going to happen is when we start doing circuit analysis, you're not going to know what the potential differences are, but you make an assumption of a polarity, and no matter what, you can't get it wrong because you make an assumption and then you find what the magnitude is. So now that we've defined voltage, let's revisit power. So recall that power is dW dt. So using the chain rule, we can split this up into two quantities. So we just saw that voltage was actually defined as dW dq. We also know that current is dq dt. So we can see that applying chain rule, we can get dW over dt by multiplying those two quantities together, where the first one is voltage and the second one is what we defined as our current. In other words, P then can be rewritten as voltage times current, VI, more generically with scripts. In other words, 1 watt can then be related to being 1 volt times 1 amp. Note, though, power, because voltage and current can be either positive or negative, likewise, power can also be positive or negative. In other words, power can be absorbed or generated. So which is which? So does positive mean absorbing or generating? So we use something called the passive sign convention to define this. Okay, so the passive sign convention is a way for us to handle the definition of generation or absorption of power. So again, let's go back to the basic two-terminal element. I'm going to write it this way this time. It doesn't really matter how I orient my terminals. So we'll say two-terminal element. And I'll arbitrarily define terminal A and terminal B. Again, what goes in must come out, so if I define current I going into A, current I is going to be coming out B. Okay, must flow through. And then I define the potential difference between A and B based on this definition as being A is V positive, is V higher than B in volts. Okay, so we do this because positive current is defined in the direction of positive charge flow. In other words, the opposite direction of electrons. So if current is moving from A to B in that direction, we're implying that electrons are moving the other direction. Because of that, we know that since electrons are negatively charged particles, they're going to be attracted to the positive polarity. Therefore, V must be defined as A is positive with respect to B. In other words, current goes into positive terminal and out of the negative terminal as defined by the voltage polarity across the element. And then so based on this, we're going to define that positive power is what we mean by being power absorbed. Negative power would be power generated. That's because if we get a positive power, it implies we have both positive V and positive I, which would be the scenario I just described, or both negative voltage and negative current, which everything is just flipped, so that's the equivalent definition. So that means that we require energy in order to move the charge as given by the drop in potential between points A and B. If you happen to get a negative power, meaning it doesn't fit this passive sign convention, it means that the element is capable of generating energy. Okay, we haven't talked about any elements that can do either of these things at this point, but that's really what our definition boils down to. And the reason that we use the word passive in this definition is because these elements that end up resulting in positive power are passive in nature in that they cannot generate energy but only absorb.